All right, welcome to Chapter 4, Section 2, Solving Exponential Equations and Inequalities is what the rest of that title was. So this is for Integrated Math 2 or IM2. The first thing you'll see on your screen is a due date. I don't see that on my screen, but you'll see it on yours as a student. Attempts just tells you that you have unlimited attempts here. I'm on attempt 1 of unlimited. You can come in here and submit this assignment as many times as you would like. We don't limit that. This particular assignment has 6 questions on it. Grading policy is always best score. Whichever one is your best for your attempt is one you keep. Partial credits enabled, so if you answer 1 of 6 questions, you get credit for the 1 question. This down here says if you start your homework, you have to finish it before you do anything else, which means if I click start, down here in the bottom right corner, I need to make sure I click the submit assignment button before I leave or go anywhere else. So you don't see it on my screen because, again, this is the teacher preview, but you will see it on your screen. So just make sure whenever you leave, even if you haven't started anything or if you've only done a couple, you click the submit assignment button. It will remember where you are and it'll start you back where you left off. So it's not going to make you redo anything. And on the side here, we have some tools. So the calculator will be open a little bit more often now that we're getting into some, exponential type equations and things like that. But these 3 are always here. So we have explanation. This is going to take the question attempt away because it's going to give you the solution to this question. So it's not going to give you the solution and let you come type it in. You'll have to come try that on another attempt. An example will just show you an example of what they expect you to be doing for this problem. So you can scroll down, read through, what does it expect for me in this problem type. You can close this and open up another example. You can keep doing that as many times as you would like. And then Message Center, so you can message your teacher from this screen. It'll attach a picture so that your teacher knows exactly where to come and help you. All right, let's go ahead and get started here. So with this one, we're looking at this equation or this situation. So suppose that $4,500 is placed in an account. So we start, this is a starting point. And I tend to like to point out these things because whether we're working with quadratics or linear or exponential, a lot of the time we can identify a couple simple pieces that help us build an equation or help us build the kind of the situation that's happening here. It's placed in an account and it pays 8% each year. And it says compounded each year. Compounded means when interest is added back to the account and you're making interest off the interest. So in this case, the 8% is added back at the end of each year, and then you start making interest off of it. So if it says compounded quarterly, that's 4 times a year. So we can think of quarters like in a dollar. If it's compounded semi-annually, that means twice a year instead of annually. Weekly would be 52 times, right? Because there's 52 weeks in a year. Monthly would be 12 times because there's 12 months in a year. So it depends on what words they use here. I think for this first one, they're going to be a little bit simple about it, and it's just going to be compounded each year. So we're going to assume that there's no withdrawals found or no withdrawals made in the account, and we're going to follow these instructions for these ones. So find the amount of interest, the amount in the account after year number 1. So without having the interest formula, we're just going to take a look at this amount. So we have this much in here, and I earn 8%. So I'm just going to do my calculation. How much did I earn? So 4,500 times 8%, and there isn't a percent button on here. I know on the smart calculators there is, so make sure you move that over so that it's 8%. So you're not multiplying by 8, you're multiplying by 8%. That's definitely going to give you a different number there. So we made $360 in year number 1. Now, is that the amount in the account? No. We started with 4,500 and we made $360. So we need to add those back together. So I need to go back over here and go plus 4,500. That is the amount in the account after year number 1 is $4,860. Now I can do year number 2 because now I have this total. This is my new starting for year number 2. So now this is the amount I'm going to make 8% off of. So now I can go times 0.08. Oops. And I hit times again. There we go. So I made $388.80. Again, that's not the amount on the account. I had the $4,860. Well, I don't know where I put my my comma in the wrong spot there, plus 388.80 equals, so I have to go over here and I have to go plus the 4,860. So this is the amount in the account after year number 2, $5,248.80. And it says right here, do not do any rounding. So if that came up at all, you would not round anything. You would just leave it exactly the way it was. So this is the idea of doing it kind of 1 year at a time. This can definitely be very tedious. If you wanted to know how much money was going to be in the account after 10 years, you'd have to do this 10 times. So is there kind of an easier way to do this? Yes, of course there is. There's a formula we can use. So we're going to start to look at this, and here it is. This is the formula. And this is very similar to what we were just writing on section 1 at the end for the exponential functions. So we have our starting point, and we are going to multiply that by the percentage. If you notice, it was 1.9%, and now it's 1.019. It's because it's 100% of the 600 and 1.9%. So it's in addition to the 100%, it's a growth. If it was a decay, then it would actually be subtracted from 100. So we'd see a percentage in here less than 100 because it would go down, it would decay. And then t is our time, and this is going to be our exponent here because for every year it's going to grow that same amount. And we were doing this on the last one. So if I'm thinking of this, if this is $600 put into account, and the first year I make 1.19%, this is how much I made. And for the next one, I'd have to have the 600 plus this. So I'd have to go like this times 1.9%. And I'd also have to add that back together too. And the next year, I would have another 1.9%. So each year I get another 1.9. So year 1 I have 1. Year 2 I'd have 2 of these. Year 3 I'd have 3 of these. Each year I make that same percentage back to it. So that's why we use that exponent that of t, because that's what's changing. That's our variable amount. So this is not the best illustration because I'm not showing it being added back each time. We want to find the current price of the list item and the price 9 years from today. So, and I kind of already gave that away. This is the starting point. We're multiplying the starting point by the percentage. So the current price is that 600 that we see at the beginning there. And then 9 years from today, we're going to have 600 times, instead of just 1.9%, we want to use that whole percentage. So this is, if we were to put this out, it would be 101.9%. Because it's 100%, it's the 600, and it's another 1.9% included. And the t is going to turn to a 9 here. So let's go ahead and use our calculator. We have 600 times 1.109, and that's going to be raised to the 9th power because there's 9 years worth of this percentage happening. So let's go equals, and it says round to the nearest dollar if necessary. So here's the nearest dollar, and there, well, I'll even go like that. So these are all the pennies. That 710 is the nearest dollar, but 7 is bigger than 5, so it's going to round up to 711. All right. So let's see, an amount of 47,000. Gosh, dang it. There we go. 47,000 is borrowed for 14 years at 3.7%. And we have 14 years. So we're going to probably use these three numbers pretty quickly here. It's compounded annually, which means the interest is added back every year, not any sooner than that, so we don't have to worry too much about it. If the loan is paid in full at the end of that period, how much must be paid back? So it says borrowed. We might think of this as a decay, but this is definitely growing. The longer we borrow money, the more we will owe on it. And that's actually what companies want from you. They want your interest. So this is a growth. So we're going to add this to 100%. So we're going to get 103.75%. And then we're going to change this into a decimal. I'm going to move it 2 times. So I'm going to have 1.0375. So this is my growth rate. So I'm going to have my starting point times my growth rate. And then that would be to the t here for the years, but I already know what the years are. It's going to be 14. So let's go ahead and type this guy in here. So we have 47,000 times 1.0, oops, I forgot my decimal, 0.0375, and that's going to be raised to the 14th power. And it says round to the nearest dollar again, so here's all my cents. That's a 1, so I can just boop, delete these guys off. And here's the amount of money. So it's a $78,000. That seems really, really high. Let's see. Hopefully that calculation came out right. Let's check. All right, so that's good. So 14 years, I borrowed $47,000 and I end up paying $78,000 back. That seems pretty darn hefty for the interest, but that's 3.75% interest is actually not that high. So if you think about, how interest works, you end up paying quite a lot of money back in interest. So this is definitely a test in our knowledge on interest and how that works. And it grows very quickly when we're doing interest. So Jane borrowed $8,000 this time, and it's a rate of 7,000 or 7%, like that. And it's compounded semi-annually. Ooh, so now we have a little bit more to think about when we're doing semi-annual. Now we can't just do annual. We actually have a little bit more that we have to take into account when it's a semi-annual type idea. And I think when I was doing this one on the notes page, I believe, let me take a look, it says quarterly. So it just depends on, the problem, what they give you here. So quarterly, we'd have a 4 to deal with because that's 4 times a year. Semi-annually is twice a year. And this is talking about 4 years. So with this one, we have an interest formula, and we click on here, we can actually see the interest formula. So this is the compound interest formula right here. So we have A equals P times 1 plus R divided by N times N to the T. So we have all these pieces. So this is our principal. This is our starting point. So this would be our 8,000. The 1 has to do with the 100% plus the rate. We want to make sure we move this over like this. So we have 0.07 divided by N is the new piece here. So we haven't had this part before because we've been doing the either add to 100 or subtract from 100. But now the N has to do with the compounded piece. So it's compounded twice a year. So we put 2 in there. So for this one, it says monthly. That's why they're dividing by 12. So it just depends. And then we have that same N on the outside. So 2 times, and it's 4 years for this one. I didn't write down years, darn it. Years. So the pieces that definitely change, we had the percentage, which we were given. We had the 4 years, which we were given. The 8,000, which we were also given. But the piece that now is brand new that we were not given is this 2 that we have to pay attention to. And that has to do with each year it's compounded or added back to the total twice. So that's just a piece that we have to know about now. And there's definitely a lot of these words. If it comes up on your problem and you don't necessarily know what that word means, definitely look up the definition of it so that you know what it means, because otherwise you can't move forward on what that number should be filled in with. So let's go ahead and type this guy in. And nicely enough, this calculator can take all of this information at once, plus, 0.07 divided by 2. Boom, like that. And then I can raise that 2 times 4. So I can do all of this at once, and I can just hit enter. So that's kind of nice. I can type that whole thing in there, and it says round to the nearest cent. So I want to go out 2 decimal places. That's a 2, so it's just going to round down. It's just going to drop off of there. So after 4 years of borrowing $8,000, she will end up paying $10,534.47. And the more it's compounded, the more it grows because the interest is earning interest. So if it's only compounded annually, it's going to grow a little slower than semi-annually. And on the example, it was growing monthly. That's going to grow faster because every month the interest is being added back, and that helps it grow even faster. It just depends on, you know, what kind of account you're given. So these seem to be loans. We're borrowing money, but if you have a savings account, a lot of the time your interest is added back every month. It's not a lot of interest. You have to have quite a lot of money in a savings account for it to have, you know, a decent amount added, but every month there is interest added to your account. And once it's in there, then it starts to accumulate its own interest. So it's just definitely a different kind of idea there. Interest earning interest. All right. So we're going to go with this one. A can of soda is placed inside a cooler. As the soda cools, its temperature in degrees Celsius after t minutes is given by this equation here, so by this function. So we have C of t equals 24 times 0.94% t. So if we think back on what we've been doing now for the last few problems and even the last few sections, we have a starting point, we have a percentage, and we have time. And usually that's time in years, but this is going to be time in minutes for this situation. So if this percentage is less than 100, that means it's a decay, right? It's going down. So if we want to know what the decay is, I'm going to take this piece, I'm going to say 1 minus 0.94, and I get 0.06, which if I moved that, it's 6%, right? So this is showing me, so I'm breaking this down, and I'm doing this specifically because that's what they're asking us for, all of these pieces. We need to think about what do we know about this problem. So now let's go over here and say, find the initial temperature. All right, well, my starting point was 24 degrees. That's what I started with. It's decaying because this is not 100%. It's less than 1. So that's a decay. And it's decaying not by 94%. It's decaying by 6% each minute. Remember, we subtracted that from 100. So that's why we had to subtract from 100 again just to see what the difference was there. And that means that it's 6% that it's going down by each time. All right. One more of these guys. Okay. So this is a little bit kind of a different exponential type equation. So when we have ones like this, what we need to do is make the bases. What I mean by the bases are these guys. I need to make the bases match. And once the bases match, I can focus on the exponents. I have an equal sign. I know that the left side equals the right side. I already know this. So what I want to do is I want to make them equal the same base, so then I can focus on the exponents. So with this one, I can break down into 5 and 5. This guy can do 5 and 25, and then 5 and 5. So, ooh, they can break down all into 5s, can't they? So with 25, I can rewrite that as 5 squared, and it already has the x plus 2 here. I have to make sure I include that. That's already there. Equals, and this guy is going to be 5 cubed because there's 3 of them. So now I have the matching base here. So if I know they're equal to each other, I can say that these exponents are also equal to each other. So I have 2, and I'm going to stop with the color coding just because it's a little time consuming. I don't think it's necessarily relevant right this minute to keep color coding this piece. So now I know if the bases are 5 and 5, and again I have this equal sign, they have to equal each other. So I want to know, okay, well, what does x need to be in order for it to equal 3, since it has to equal this other side? So I'm going to go distribute this, and I'm going to 2x plus 4 equals 3. I'm going to subtract 4 from each side because now I can start solving. 2x equals, those guys canceled. Sorry, I didn't say it, but they canceled. 3 minus 4 is negative 1. Divided by 2, divided by 2. X has to equal negative 1/2 in order to make this true. So that's what x needs to be is -1/2. All right, so that was section 2. I will see you in section 3.